This is my revision video. It's not everything, so the job is still down to you, but here's a few pointers. So we started with forces and motion. We first started off with the scalar equation for speed, and as you all remember, speed is distance over time. And later on we went on to a vector quantity, which was velocity. And if you remember, a vector is something that has size and direction. And so in this case, we use displacement over time. And that can give us a really odd result, that if we do something like going in a circle, we use the example of the racetrack, you can actually have an average velocity then of 0, because at each point you can imagine thousands of arrows, and each arrow cancelling out the other arrow, like so. So that's speed and velocity. Next we went on to acceleration. And acceleration we saw as the change in velocity in v over the time for that change. Now the equation can be written algebraically like this: v minus u over t. And this is the change. Velocity at the end, velocity at the start. The unit is meters per second squared. We can then graph this acceleration, and if we take a simple one and we go across here and across and down, at each point we can take v and we can take u, we can divide it by the time t right across, and we can calculate the acceleration at each point. But more importantly, and the real reason behind using a graph, is that we can also calculate the area underneath by bisecting it into triangles, half base times height, and rectangles and squares. So by finding the area under the graph, you'll find the total distance travelled. Next, the work done equation. I like this equation because it lets you turn energy, work done, from a force. So it's the equation that links energy and force together, and it's as obvious as you can make it, really. The harder something is to push, the further you push it, the more energy you're going to use. The other equation we're going to use is the momentum one, the idea that an object in motion wants to keep moving, and again that's just down to its mass times its velocity. The unit on this one's a bit weird. We have mass in kilograms, we have velocity in meters per second, so very unimaginatively it's kilograms meters per second. Next, force. We've got that old equation, mass times acceleration, and we get this idea of resultant force. So typical question might be something like this rocket. We might have 5 newtons heading up, 3 newtons in weight, and what we've in fact got then is a resultant force of just 2. And it's this number that we would be plugging in if we were calculating mass or acceleration. This is the force we would use. There's a spin-off of that, which is weight, and again it's a force, so again it's just mass times, and this time it's the acceleration due to gravity. So we just put g, and usually it's 9.81, and in any exams you'll always be told what to assume it as. Some people go with 10, some 9.81, it's up to you. Next, free fall. This question is concerning the idea that on a body in motion, free falling, you have 2 forces. You have weight and you have air resistance. When you initially fall out of the plane, let's get this right, your weight is constant, you have little to no air resistance at that split second, so you have a large downwards resultant, and if we were to graph this on the side, it would be a big acceleration on a velocity time graph. As you continue to fall, your air resistance is going to increase, your resultant is eventually going to fall to 0, and at this point your forces will be balanced. And we can see on our graph that's slowly going to bring our graph across till we reach terminal velocity. You continue to fall. At this point you really want to slow down, the ground's starting to come up quick. So you pull your parachute, and now your air resistance becomes massive. You have an unbalanced force acting in the opposite direction. That is going to cause a massive deceleration. So again, we're going down like so. But as you slow down, your air resistance is going to decrease. And eventually it's going to decrease until, again, it's balanced. So at this point you've reached a new terminal velocity, and hopefully this one's slow enough that you can land safely. So you'll need to know all about unbalanced and balanced forces, and the shape of this graph and what each part is telling you. Finally, flying with balloons. This was a practical I set you guys. A little worried that quite a few people didn't do it. Got a little too balloon crazy. The idea being that acting on a balloon is the upward lift force from the helium. And we can find that force by using the equation weight is equal to mass times gravity, where the weight is exactly cancelled out by this force. So if we can find the weight, we've found the force that was pulling upwards. To find the weight, we're going to need to find the mass. So we popped it on some scales, we took the blue tack and the string that was pulling downwards, and we weighed that string and blue tack. Once we knew the mass, we could use mass times 9.81. That would tell us the weight acting downwards. Once we knew the weight acting downwards, we know that that is equal to the force acting upwards. And then the final step is finding our weight in newtons, and we can then just divide our weight by the force of one balloon, and that will give us the number of balloons that we need. Okay, that's just a quick helper. It's a guideline to help you. You've got to do the hard work though. Watching this alone isn't enough. Have a go at some practice questions, rearrange, and I will see you all on Monday, and good luck with the test. Bye.